Ever get that feeling like you just want to instantly grasp those seriously mind-bending ideas? The kind everyone's always talking about. Like just play in and bam, you get
I
it.
know exactly what you mean.
Well, that's kind of what we're going for today.
Oh, ambitious. I like it.
Yeah, we're taking a deep dive, a proper deep dive into something that's truly bizarre.
Sounds promising already.
But it's fundamental, like truly fundamental to how the universe works. Quantum entanglement.
Oh yeah, quantum entanglement. That's a big one. It really challenges how we think about reality, like at the most basic level.
Exactly. So for those who haven't encountered this yet, what is this quantum entanglement all about?
Well, you can think of it this way. It's like when two or more tiny particles, and I mean really tiny, like subatomic particles, get linked up.
Okay, linked up how?
Linked up in a way that their fates are intertwined. Their properties become correlated, so if you measure something about one of them, you instantly know something about the other one.
No matter how far apart they are.
Doesn't matter. Could be across the room, could be across the galaxy. And that's what spooked Einstein, right? He called it spooky action at a distance.
It does sound kind of spooky when you put it like that.
Mm.
So we've got this source material, this quantum entanglement.pdf, and it really dives deep into this idea. It says it's not just some coincidental connection. It's like a deep fundamental link between their quantum states.
Right. It's really about their very essence, their quantum essence being intertwined.
Okay, so let's break this down a bit. What's this whole wave function thing about?
So in the quantum world, these particles aren't just sitting there like little billiard balls with set properties. They're a bit more elusive than that. They're described by what we call a wave function.
Okay, a wave function. Sounds complicated. What does that even mean?
Think of it like a menu of possibilities for the particle. It describes all the possible states that particle could be in. It's not fixed until we try to measure it.
So it could be here, it could be there, it could be spinning this way, it could be spinning that way.
Oh, yeah.
It's all up in the air until we take a look.
Exactly. It's a fuzzy cloud of possibilities. It's only when we measure it that the wave function collapses and the particle chooses one definite state.
Ah, I see. So how does entanglement fit into this whole wave function picture?
Well, when particles get entangled, it's like their individual menus of possibilities merge into one super menu. They start sharing a single wave function, at least for some of their properties.
Oh, that's where it gets really strange.
Yeah.
Okay, so let's try and picture this. Let's say we have two entangled particles, and they have this property called spin, which can be either up or down.
All right. Two entangled particles with spin. I'm following.
So if we measure one particle and find that it's spinning up, the other one, even if it's billions of light years away, will instantly be spinning down.
Exactly. It's like they're connected by an invisible thread. But here's the kicker. Before you make the measurement, neither particle has a definite spin. They're in a superposition, a mix of both up and down at the same time.
It's like they haven't made up their minds yet.
Precisely. And it's the act of measuring one particle that forces both of them to choose a definite state. And those states are always opposite.
Okay, I think I'm starting to get it. But how do they actually become entangled in the first place?
Well, there are a couple of ways this can happen. One way is through direct interaction, like if the particles collide.
Makes sense. They bump into each other, some quantum magic happens, and boom, they're entangled.
You got it. Another common way is if they're born together, emitted from the same source at the same time.
Our source mentions something called spontaneous parametric down conversion. That sounds a little
It's a
intimidating.
mouthful, right? But the concept is actually pretty cool. You take a photon, which is a particle of light, and you shine it into a special type of crystal. Sometimes this photon splits into two new photons, and these two new photons, they're entangled. Often they're entangled in terms of their polarization.
Polarization, that's like the direction their electromagnetic field is vibrating, right?
You got it. Another example is two electrons within an atom that are sharing the same energy level. Their spins can become entangled because they're part of the same quantum system.
Okay, so they either interact or come from the same source, and then boom, entangled. What happens at the quantum level when they become entangled?
Well, our source actually give a little peek into the math behind it, just a little peek. Physicists represent this entanglement with a mathematical expression called a wave function. And don't worry, if you're not a math whiz, the idea is what matters. So for our two entangled particles, A and B, their combined state might be represented by something like this. So Pofro, wrangled, down arrow, now no, praco, yao, or one, powero,
Oh,
one.
whoa. Okay, that looks like something out of a physics textbook, which is fine because it is. Can you decode that for the rest of us?
Sure, it's basically saying that the particles are in this blurry, undecided state. Until we look, We don't know if A is up and B is down, or the other way around. They're both possibilities at the same time, but the key thing is they're linked. If one is up, the other has to be down. That minus sign, you see, it's important. It tells us about the specific type of entanglement. It means they're linked in a way that their spins will always be opposite.
Okay, so before we look, they're in this hazy realm of possibilities. But as soon as we peek at one, bam, everything snaps into focus and we know the state of the other,
Wow.
even if it's miles away or, light years away, like you said. That's what really bothered Einstein, wasn't it? This spooky action at a distance that seemed to defy the speed limit of the universe.
It really did. The idea that something happening here could instantly affect something way over there, well, it just didn't sit well with him. It seemed to contradict his theory of relativity, which says nothing can travel faster than light. And the other thing that really bugged Einstein was the idea that these particles didn't actually have definite properties until they were measured. It wasn't just that we didn't know, it's that the properties themselves were genuinely undetermined.
Okay, so it's not like they had some secret set of instructions, like hidden variables, that determined what they would do when measured.
Nope, that's the weird part. The quantum world is fundamentally probabilistic. It's all about chance and uncertainty until we make that measurement.
So does that mean that entanglement actually violates Einstein's theory of relativity?
Hmm.
Because if information can travel instantly, wouldn't that be faster than light?
That's a great question and a common concern. But the good news is, no, entanglement doesn't actually break relativity. The source is very clear about that. While the correlation between those particles is instantaneous, we can't use it to send information faster than light.
Okay, that's a relief, but how come? If I know the state of one particle instantly, can I somehow use that to send a message faster than light?
Here's the catch. While we know that the particle states are linked, we can't control what state we'll get when we measure one of them. The outcome is completely random.
So it's like rolling a pair of dice that are somehow quantumly linked. Even if they always land on opposite sides, you can't choose to roll a 6 on one die and instantly force the other to roll a 1. You know they're going to be opposite, but the actual outcome is still random. Is that what you're saying?
Precisely. That's a great analogy. So to actually confirm the entanglement and see the correlation, you and someone observing the other particle would still need to communicate your results. And that communication would have to happen through normal, slower than light channels.
Wow.
So no faster than light messages, even with spooky action.
Okay, that makes sense. So Einstein and his buddies thought this spooky action meant quantum mechanics was incomplete. They thought there had to be these hidden variables that determine the particle states all along. But how did physicists move beyond this philosophical debate to something they could actually test?
That's where a brilliant physicist named John Bell comes in. Back in 1964, he came up with a clever way to test this whole hidden variables idea. He formulated what are known as Bell's inequalities, these mathematical rules that would hold true if those correlations we see were actually due to hidden predetermined states.
So if experiments showed that these Bell inequalities were being broken, that would be a pretty strong sign that hidden variables weren't the answer, right?
Exactly. It would mean that the correlations were genuinely quantum and couldn't be explained by any kind of pre-existing instructions. And guess what? That's exactly what happened. Early experiments by Clauser and Friedman back in the 70s, and then even more convincing ones by Elaine Aspect in the 80s, they all showed that Bell's inequalities were being violated.
They actually saw these inequalities being broken. So the experiment supported quantum mechanics and ruled out the idea of local hidden variables.
Exactly. They basically said, hey, Einstein, sorry, but the universe is even weirder than you thought. The experimental evidence was so compelling that it really forced physicists to rethink their understanding of reality.
Our source mentions that there were even more recent tests, like in 2015, that closed loopholes in the earlier experiments. What were those loopholes?
Right. So while those early experiments were pretty convincing, there were still a few niggling doubts. Some physicists wondered if maybe there were some subtle ways that the particles could be communicating with each other in a classical non-quantum way. Or maybe there were issues with the efficiency of the detectors that were being used. So in 2015, they did these super careful experiments that closed all those remaining loopholes, providing even stronger evidence for quantum entanglement.
Wow, so they really went the extra mile to make sure. So this isn't just some philosophical debate anymore. Quantum entanglement has been rigorously tested and confirmed through experiment. That's got to have some pretty huge implications for how we think about the universe, right?
Absolutely massive implications. It challenges our everyday understanding of reality on so many levels. It suggests that the world is far more interconnected than we ever imagined, and that our classical intuitions about how things work, well, they often just don't apply at the quantum level.
It's like the universe has these invisible threads connecting things together in ways we can't even begin to grasp with our ordinary senses. So what are the philosophical takeaways from all of this? How has entanglement changed how we think about the universe?
Well, it really undermines two key concepts that we take for granted in our everyday lives. The first is realism, the idea that objects have definite properties whether we're looking at them or not. Entanglement suggests that this isn't always the case. Properties can be fuzzy and undefined until they're measured. The second thing it challenges is locality, the idea that things can only influence each other if they're close enough for a signal to travel between them. With entanglement, the influence seems to be instantaneous, no matter the distance.
So the universe is far weirder and more interconnected than we ever imagined. It's a real head-scratcher. Our source even mentioned different interpretations of quantum mechanics, like the Copenhagen interpretation and the many worlds interpretation. It sounds like physicists are still wrestling with the implications of entanglement and what it means for our understanding of reality.
They certainly are. It's one of the most fascinating and hotly debated topics in physics today. But entanglement isn't just a theoretical curiosity. It has real-world implications, too. In fact, it's playing a starring role in the development of some seriously mind-blowing technologies.
Right? Like quantum computing. Everyone keeps saying the quantum computers are going to revolutionize everything. So how does entanglement fit into all of that?
Entanglement is absolutely essential for quantum computing. You see, quantum computers use these things called qubits, which are like the quantum version of bits in a regular computer, but unlike a regular bit, which can only be a 0 or a 1, a qubit can be both 0 and 1 at the same time. It's in a superposition, just like those entangled particles we talked about. And when you entangle multiple qubits, you can get them to work together in a way that allows for massive parallel processing.
So the more entangled qubits you have, the more powerful the quantum computer.
That's the basic idea. And that parallel processing means that quantum computers can tackle certain problems that would take even the most powerful classical computers billions of years to solve. They could revolutionize fields like drug discovery, material science, and artificial intelligence.
Wow, that's incredible. But what about quantum cryptography? I've heard that entanglement can be used to create incredibly secure communication systems. How does that work?
It's a really neat concept. In quantum cryptography, two parties share a stream of entangled particles. The key is that any attempt by an eavesdropper to intercept those particles and snoop on the communication will inevitably disturb the entanglement. And because entanglement is so delicate, that disturbance can be detected by the legitimate parties, letting them know that someone is trying to listen in.
So it's like a built-in alarm system that goes off if someone tries to tamper with the message.
Exactly. Our source even mentions China's Mises satellite, which has successfully used entangled photons for secure long-distance communication. It's a real-world example of entanglement being used to enhance privacy.
That's amazing. So entanglement isn't just theoretical anymore. It's being used for real-world applications right now.
What about quantum teleportation? Is that something we're actually close to achieving? Can we beam ourselves up like on Star Trek?
Not quite yet, but quantum teleportation is a real thing, and it's pretty amazing in its own right. It's not about teleporting matter, it's about teleporting information.
Information, what do you mean? It's about transferring the quantum state of a particle from one place to another without physically moving the particle itself. So imagine you have a particle in a particular quantum state. You want to send that exact state to someone far away. You can use entanglement to do that.
Okay, I'm intrigued. How does that work?
You need a pair of entangled particles, one at the sender's location and one at the receiver's. Then you perform some clever measurements on the original particle and the entangled particle at the sender's end. You send the results of those measurements to the receiver via regular communication channels. And here's the cool part. The receiver can use that information to reconstruct the exact same quantum state on their entangled particle. It's like the information about the quantum state has been teleported.
So it's not about beaming up the physical particle itself, it's about replicating its quantum state somewhere else. That's still pretty mind-blowing. And our source says that they've already managed to do this over hundreds of kilometers.
Yep. It's one of those things that sounds like science fiction but is actually becoming a reality.
Okay, and finally, what about quantum sensing and metrology? How can entanglement help us make more precise measurements?
Entanglement offers a way to improve the accuracy and sensitivity of measurements beyond what's possible with classical techniques. You can think of entangled particles as being super sensitive to tiny changes in their environment. By carefully preparing these entangled states and making clever measurements, we can detect incredibly subtle changes in things like magnetic fields, gravitational fields, and even time itself. It could have huge implications for fields like navigation, medical imaging, and fundamental physics research.
It's amazing how this one concept, entanglement, has implications for so many different areas of science and technology. But I imagine it's not all smooth sailing, right? There must be some serious challenges involved in actually working with entanglement in these practical settings.
Oh, absolutely. Entanglement is a finicky beast. One of the biggest challenges is something called decoherence. You see, those delicate entangled states are easily disrupted by their surroundings, by things like stray electromagnetic fields, and even just bumping into air molecules. It's like trying to build a house of cards in a hurricane. It's a constant battle to keep those entangled states stable long enough to do anything useful with them.
So it's incredibly powerful, but also incredibly fragile. That makes sense.
Yeah.
Now, I always love the fun facts and recent developments section in our source material. What are some of the more intriguing things that are happening in the world of entanglement research right now?
There's so much exciting stuff going on. One of the most fascinating areas of exploration is whether entanglement might play a role in biological systems. Some scientists are investigating whether it might contribute to the efficiency of photosynthesis in plants or even help birds navigate using the Earth's magnetic field. It's called the quantum compass hypothesis. Now, it's important to note that this is still very speculative, but the idea that quantum effects might be at play in living organisms is incredibly intriguing.
Quantum bird brains. That's wild. What else is going on?
Another cool development is entanglement swapping. This is where you can entangle two particles that have never directly interacted with each other by using a third, intermediary pair of entangled particles. It's like creating entanglement by proxy, and it's a key technique for building larger and more complex quantum networks.
So you could theoretically create a whole chain of entangled particles, even if they're spread out across vast distances.
Precisely. And speaking of networks, there are some serious efforts underway to build prototypes of a quantum internet. Imagine a network where information is transmitted not with classical bits, but with entangled qubits. It would be a fundamentally new way of communicating that could offer unprecedented levels of security and speed.
A quantum internet. That sounds like something straight out of science fiction. What a game changer that would be.
It would be revolutionary. And then there's one final fun fact that really blows my mind. It's this idea called the EPR conjecture.
Okay, that sounds mysterious. What's that all about?
It's a pretty deep and complex idea, but essentially it suggests a connection between entanglement and wormholes. Remember those entangled particles, those links across space? Well, the EPR conjecture suggests that these links might actually be related to the structure of space-time itself. In some extreme cases, these entanglement links could even give rise to wormholes, those hypothetical tunnels through space-time that could connect distant parts of the universe. It's a very speculative idea, but it hints at a profound connection between the quantum world and the fabric of reality itself.
So those tiny invisible threads connecting entangled particles can be woven into the very fabric of the universe. That's a truly mind-bending thought.
It certainly is. Entanglement is one of those things that just makes you realize how much we still don't know about the universe. It's a constant reminder that reality is far stranger and more wonderful than we could ever have imagined.
So to quickly sum up our deep dive today, we've seen how quantum entanglement creates these unbreakable links between particles, linking their fates across vast distances. While it initially seemed like it might violate Einstein's theory of relativity, it turns out that's not the case. We can't actually use it to send information faster than light. We also explored the experimental evidence that confirms the reality of entanglement, showing that those correlations are genuinely quantum and not due to some hidden pre-existing instructions.
And we talked about the amazing potential of entanglement for real-world applications like quantum computing, ultra-secure communication, teleportation of quantum states, and incredibly precise sensors. It's a field that's full of challenges, but also full of potential, with some truly mind-blowing possibilities on the horizon.
It's like looking through a keyhole into a whole new reality, a reality where the rules of the everyday world no longer apply. And who knows what other mysteries and wonders entanglement might hold. It's a thought that should keep us all pondering for a long time to come.
Absolutely. The exploration has just begun.
It really has.